Hi everyone, this is Derek Katsia, and this is part 2 of our video tutorial on the Stencil Specializer, which is one of the most well-developed specializers that uses Asp SEJITS. And today I'm going to talk a little bit more about stencils, and then I'm going to dive into what kind of constructs we can put inside the stencil kernel function, and how we represent that inside the Stencil Specializer. So what we're looking at here is just the beginning of the Wikipedia article on stencils, which is they call stencil code. And this describes briefly some of the other applications. So last time we saw an image processing application, and it's definitely useful for that. But there are a lot of other applications. They're used in computer simulations like fluid dynamics to describe how elements flow between cells of a region. You can have both two-dimensional and three-dimensional grids. You can use them to solve partial differential equations. You can use them to describe cellular automata, like the game of life, if you've seen that. So stencils have a lot of applications beyond simple image processing, and I'm focusing on image processing in this tutorial mostly because it's really easy to visualize the input and the output of our operations so that we can kind of visually confirm that we're getting what we expect. But these definitely have diverse applications, and that's why it's useful to have a specializer that targets this kind of problem, because they really have diverse different uses and applications that you can place it in. So we're going to move now to our code. So the first thing we're going to do is we're going to look at several different kernel functions, and we're going to kind of see how they're similar and how they're different, and that'll help us describe the language of kernel functions. So it's important to note here we don't want to accept just any valid Python into our kernel function, because we wouldn't know how to compile that into efficient C++. That's a really hard problem. But if we constrain the language to some reasonable subset of Python that we know describes a stencil kernel, and that we can always compile down to efficient C++, then that'll enable us to get efficient code. So we're starting with this blur average function that we saw last time, where we're just taking the 4 surrounding points in an image and we're averaging them to get the corresponding point in the output image. So we're looping over the interior points, we loop over the neighbors, and then we do some arithmetic on the input points to get the output points. So that's pretty straightforward. So the first kernel I want to talk about that's a little different from this is the copy kernel. This is just the very simplest kernel almost, that just loops over the interior points and copies the input points over to the corresponding output points. And the way we're going to do this, we loop over interior points, and for each point we just get the point at x and we assign it to the point at x. So the important thing to take away from this is you don't always have to have a neighbors loop, and you can reference the input image inside of the outer loop by using x, even if you don't have a neighbors loop. The next kernel we're going to look at is a little bit more complicated. So this simple 4-point blur is fast, but it's not very high quality, and it only induces a little bit of blur. So an interesting question is if we can get a more high quality Gaussian blur, meaning that we have a blur where we're taking pixels in a larger region around the point into account, and we usually treat nearby points, give them a higher weight, and then further away points we're going to give them a smaller weight, and it drops off rapidly as you move away from the point. So the way that we're going to do this is I'm not showing the code here, but we've redefined the point set 1 to include a lot more points in the neighborhood of this point, probably a 3x3 region or a 6x6 region. And what we're going to do this time is we're going to pass in the input image, the output image, and this filter D. And what filter D is you know how I said that nearby points are going to be weighed more heavily than far away points. And so filter D describes the exact weights that are applied based on the distance between the output point and the input point that's being added to it. So up here in our original blurring kernel, basically we were multiplying everything by 1/4. So we were doing a uniform weighing of all 4 points. Here we're doing a different weight depending on the distance of each point from the output point. And we use this distance function to represent the distance between 2 points. Now this is really easy to write in Python. It just takes 2 points and it does the Pythagorean theorem, and out you get the Euclidean distance between the points. But it's going to be interesting how we translate this down into C++. So the next thing we do is we have this int function. So filter D is an array, and you can't have fractional indices into an array. You can't do a of 1.5. So we're going to convert it to an integer, round it down to the nearest integer, and look that up in our array of weights. So the weight's not going to be exactly perfect, but it'll be close enough. And then we just look it up in this filter D array, and that gives us our weight, which we multiply by the input point and add to the output point. So the important thing I wanted to show here in this kernel is that we have this one-dimensional array whose index is not a point, it's an expression. And this expression involves this distance function and this int function that are being applied to values that we didn't see before. In addition, this kernel demonstrates the use of the border points function, which is a lot like interior points, except it gives the other points, the points that are near the border and are not in the interior of the image. So for these points in this example, I'm just doing a copy from the input to the output. You could do something more sophisticated, but that's just to demonstrate for this example. Finally, the bilateral filter is one of our demos. It's one of the more complex filters. And this has the same filter D mechanic as before. So we're dropping off the weights with distance. But on top of that, we're also making it so we have this filter S. And what filter S does is we look at the difference in values between the input pixel at the point where we're doing the output and the input pixel at the point where we're adding. So the idea here is we want to weigh pixels that are close in value more heavily and pixels that are higher in value a lot less. And the effect of this will be that we'll end up doing a filter that tends to sharpen or highlight edges in the image without so it'll do blurring inside the edge, but it won't blur the edges. It's intended to be edge preserving. So when the difference is large, the blur will be small, and so the blur will that'll prevent the blur from blurring the sharp edges, but it'll still blur inside smooth regions, if that makes sense. So this is just an idea of some of the things that we can do. In this case, it's important to note that we're actually using these pixel values and we're subtracting them, and that's ending up going into our array index. So we need to be able to do arithmetic on these pixel values and use them as array indices. And we also need this absolute value function, which is just another one-argument function, like int, and distance was a two-argument function. So now that we've seen some examples, I want to go back to our initial example of a kernel function, which was just the blur. And I want to show kind of how we can describe this with a tree data structure. And this tree data structure is going to map directly onto the kind of data structure that we use inside of our program. So keep in mind that all Python programs are described by a tree data structure. And that tree data structure, even for very short programs, can be very large and complicated. And we don't really want to deal with a tree that's that big and complicated if we don't have to. So the idea is that we're going to use a much simpler tree data structure that's customized for the Stencil problem, and that can only represent Stencil kernels. So at the top level, we have a function, which is just our kernel function. It has some arguments, which are the grids that we pass in. Here they're in image and out image. And any particular Stencil kernel, we assert, will have at most one loop over the interior points and one loop over the border points. We don't need more than that, because we can always put more stuff inside both of these loops. So this particular function at the top only has an interior loop, so it's just going to have the one interior kernel. And this is implicitly a kernel that's looping over the interior points. And it has a body. The body says what you're going to do for each of those interior points. And what we're going to do is we have a neighbor loop. The neighbor loop loops over each of the neighbors of the current output point. Now notice how this is not actually a simplification. This is all the data that we need here, because we know that if we're doing an interior loop, we're looping over the output points. So there's some current output point, and the neighbor loop is going to loop over the neighbors of that output point. We just need to specify which input grid we're drawing the neighbors from, and the ID of the neighbor collection. So here, that's this one here, the label of the neighbor collection. Inside the neighbor loop, it has a body, and the body is just going to say assign output. So we're doing outImageX equals outImageX plus inImageY plus 4. So it's going to be a little more clear if I write this explicitly, like that. So notice that pretty much in every single one of these kernels, we're always doing outImageX equals. And you might ask, well, can you do outimage some other point equals, outimage y equals? And the answer is no, you can't really do that. That wouldn't make sense. So because we're always going to do this, we can just have a simple node that says assign output. And what it does is outImageX equals some value. And the value that's getting assigned is this expression expressed as a tree. We're going to have a sum plus the current output value, or the value of the output grid at the current output location, outImageX, which we can just represent as output. Then we're going to have a divide node, dividing by 4, and neighbor represents the current neighbor in the input image. So that's just inImageY. And this is all the information that we need to represent this kernel function. And this is going to be a lot simpler than the corresponding Python abstract syntax tree for this function. So now I'm not going to show the trees for the others because they're a little more complicated, but we're going to have nodes to represent each of these operations. To represent indexing into this one-dimensional stencil, we're going to have a node for that. We're going to have the same way that we had interior at the top here. We can have another arrow for border. We can have another kernel for that. And finally, we're going to have nodes for just functions, like applying int or distance or absolute value to our expressions. So now I'm going to show you what that looks like. This is Stencil model. Stencil model defines what we call the semantic model for the program. The semantic model represents a particular instance of a stencil kernel, and each one of these nodes that's listed in here. So notice that the first thing it does is say parse, and then it has this triple quoted string that is basically the entire file. So what this is doing, the triple quoted string ends here. So basically, we're writing inside a domain-specific language that's being embedded in Python inside of this string. And this domain-specific language is used to define a tree data structure that we're going to use to represent our program. And it's going to generate Python and automatically import that Python for us so that we can use it. I'm going to show you the generated Python in a minute, but right now let's look briefly at the kinds of nodes that we're defining and the syntax that we use to define them here. So stencil model is what I described as function here. It's our top-level node. It has a set of input grids, which includes the output grid, and each one is described by an identifier. So the star here means 0 or more, like in a regular expression. So it has some list of identifiers. Then we're going to have the interior kernel and the border kernel, which are both going to be kernel nodes. Identifier is a really simple node, just has a name, which is going to be a string. Kernel is going to have a body. The body is going to be either a loop over the neighbors or a simple assignment to the output, like in our copy example. Here we had a simple assignment to the output. And we're going to have 0 or more of those. So we could have multiple neighbor loops if we wanted. Each neighbor loop is going to specify the grid, the input grid that we're looping over. It's going to specify the ID or the label of the neighbors. So that was 1 in our example. And the body is going to be some set of output assignments. And you'll see these check things here, and what those are doing is we're basically making sure that our tree is well formed and obeys the semantic constraints of our language. Like in this case, this neighbor's ID value, it has to be, it can't be a negative value. And this is automatically checked when we're constructing the tree. Next we have output assignment. Remember that output implicitly assigns to the current output element, which is out image x in this case. And it assigns some input value to it. Now here we have expression. This one, if you've seen standard ML or languages similar to it, you would have seen something like this before. The idea is that this is a disjoint union type, and it represents that we have an expression, and the expression can be any of these values. Another way to think of it is like this is like subclassing. It's like we have an expression superclass, and these are all subclasses of expression. So the first thing is it can be a constant like 4. It can be neighbor, which represents the current neighbor element, which we saw in our tree a minute ago. It can be output element, which is the current output element. We also saw that in our tree. I'll bring up the tree for a second so you can see those. So output element was the out image x. Neighbor was the in image y. Now, these are going to be used later in the translation process. Input element represents the input element at some offset to the output element. For example, at an offset of 1 in the x direction and 1 in the y direction. And what's going to happen is these neighbor elements are going to be translated into these at a later point. You can't actually type these directly into a Python stencil program, but they're used for translation. Input element 0 offset. So this is just a special case of this where the offset is 0. And it's kind of handy to have this because we don't know exactly what dimension the grid is going to have. So we don't know how many zeros to have. And it represents cases like this where we're doing a copy. And we're copying from x. So x here is the same offset that we're looking at in the output image. So it's at 0 offset from this x. So it's like x plus 0, 0. And we're looking at that offset in the input image. Input image expression index. So this is like down here we were doing filter d int distance xy. So we have some expression inside these brackets. And expression index allows us to index into a one-dimensional input grid or input array and look up a corresponding index using an expression like that. Scalar binop, that's just a binary operation like plus, minus, times, divide, no big deal. Math function, that's going to be the things we saw like integer, absolute value. And finally, neighbor distance, which is simply the distance between the current output point and the current neighbor. And we're never going to want to find the distance between any two other points. So it's completely sufficient to just have this. For the rest of this, it's going to be pretty straightforward. We're going to have constants. We're going to have input elements that, like I said, they have offsets, which are represented as list of integers. We're going to have the 0 offset. Input elements are going to specify what grid they come from because it's possible to loop over multiple input grids at the same time in a nested loop. We're going to have our expression index. It has the grid and it has the expression. We're going to have our math function, specifies a name and a list of arguments. And we actually have a dictionary here after our triple quote ends that's going to tell us what are the valid math functions. And it'll check to see if any math function we use is one of these, and if it's not, it'll throw an error. This also specifies the number of arguments that each one receives. So these both receive 1 argument. Finally, we have scalar binary operation. So that's our whole language. And it's a very simple language, but it's capable of capturing all of the different kind of stencil kernels that we want to represent. And when we call this parse function, it's going to go to our tree grammar module, which I've imported here, and it's going to convert it into Python. And what we end up getting out looks like this. Each one of those nodes, like stencil model, like identifier, has turned into a class. All these classes inherit from ast.ast, which is basically a abstract syntax tree class that is used to represent tree nodes. They each get a constructor that lets you easily pass in the list of arguments and the list of child nodes and the line number and column, and it'll create it. And it automatically does a check, and what this check does is it makes sure that the types are what you expect. So here we have the interior kernel, the border kernel, and according to our stencil model, the interior kernel and border kernel should both be kernel objects. And sure enough, if we look at the check function, we can see that it does check that interior kernel is a kernel object and border kernel is a kernel object. And it also gives us a deep copy function, which is just handy if we want to take the entire tree and make a copy of it. So once all this code is generated, it just automatically imports this into the Python environment, and we can start creating stencil model objects. We can start creating identifier objects, kernel objects. We can just generate all of these and use them to start building up our tree in memory, representing our stencil kernel. And this tree is going to be a much sparser and simpler tree than the original tree representing the Python program. So what we're going to look at next time is we're going to take a look at the Python abstract syntax tree for a kernel function like this. And we're going to take a look at the process by which it gets converted into these stencil model objects. So I'm just going to give you a little preview. We're going to open up Stencil Python frontend. So this is the code that's responsible for taking a Python abstract syntax tree, converting it into the stencil model tree form. And it has visitor functions for each of the Python abstract syntax tree node types. And inside of these nodes, it stores some local information, and in the end, it builds stencil model object. And that stencil model object is going to have kernel objects inside it. And here we're building identifier objects. And here we're building output assignment objects and scalar binop objects. So all we're going to get out of here is a tree that uses these nodes. All right, thanks for watching, and see you in part 3.